This is Cameron Chai from azom.com, and I'm speaking to Professor Ian Bakey from Kelvin Probe Specialists, and he's going to explain or demonstrate to us their scanning Kelvin probe.
Thank you. Here, this is a scanning Kelvin probe system. The sample is aluminium and gold, and the Kelvin probe measures the work function difference between a vibrating tip here and the material under the tip. And the material under the tip could be a metal, as in this case. It could be a device, as in this case, which is a single electron transistor device. It could be a wafer with a pattern on it, and it could be different types of solar cells. And this technique is used for corrosion studies, for polymer films, for polymer electronics, and for material studies. It can detect films as small as 1 molecule, so I'm just going to show you a molecular film. You can see the pattern just disappearing because of the surface tension. That was very quick, I'm afraid, but that's a film that's 1 molecule high, and that will give a work function difference of about 350 millivolts, and our resolution is 1 to 3 millivolts. So here we have a scanning platform with a tip that I can move up and down. The tip is vibrating and produces a signal at the oscillation frequency of the tip, which is about 70 or 80 hertz. The sample moves under the tip, and we form a three-dimensional map of the work function or surface potential of the sample. And because we have an interface here, we'll see that as a big work function contrast. It's an ideal technique in the sense it gives you real millivolt resolution. Other techniques give you a contrast, but you don't actually know what the scale is. So if I can move slowly around. This is a control unit. It's digital. It drives the probe. It sets the frequency of the probe, the amplitude of oscillation, and the spacing. And this is the Kelvin probe signal. This is the closest approach as the tip comes close to the sample, and this is the point where you go farther away. We control the tip potential. In the Kelvin probe measurement, if I control the tip potential, I can make the energy of the tip and the surface the same, and at that point I'll get zero signal. That's called the null field. So as you can see, I've got a little bit of noise at null, but I've got a flat line on the oscilloscope. The traditional Kelvin probe is a null field, but as you can see, it's a noisy method, and I invented the off-null method that you measure on large signal heights. So what you do is the computer calculates where zero will be through 2 measurements, and it can go quite fast. As you can see on the oscilloscope, the measurements proceeding quite fast. It can go up to 1,000 measurements a minute, so I can do 1,000 surface potential measurements a minute. And we're working in a conference hall here, so it's a little bit noisy with people going past, but normally you'd achieve 1 to 3 millivolt resolution, which is perfectly adequate for most surfaces. It's a simple technique to use. I measured some customer samples yesterday, and the customer was astounded by how fast it was compared with the technique he was used to, which is atomic force microscopy Kelvin probe. So it's a quick technique, very fast, automatic setup, great. Thank you.
All right, Professor Bakey, thanks very much for your time.